Okay, then thanks a lot, everyone. Thanks for your patience. I'm sorry we had some small technical difficulties. So very welcome to the workshop for the Euro Meets NeurIPS 2022 vehicle routing competition. So I'll start today with the overview of the competition. Then we will have a keynote presentation by Thibaut, and then we will have a small break. So you can see the schedule on the website. I don't have it actually here in the slides. But we will have a small break, and then we will have presentations by the finalists, and then we will announce the results. After which we will have some time for interaction. And so I wasn't sure exactly how many people we would have. Probably we'll try if we can assign some smaller breakout rooms, and you can like talk a bit in smaller groups, well, to discuss everything that we learned today. And so this is basically the same presentation as can already be found on the NeurIPS website, but I will go through it, well, also to give a bit of an overview of the competition. So I don't think I need to explain you about the competition, because you've spent well, as much or like more time even than me on this competition over the past few months. But the goal of this competition was really to bring together people actually from different backgrounds, so from operations research background and from machine learning background, to work on the same vehicle routing problem. And the reason we decided to organize this challenge is that we saw that there's actually a lot of research being done in the operations research community, but also then in the machine learning community in the past few years. This has really picked up, and we thought it would be nice to sort of bring these communities together and independently evaluate the different approaches. And for that, we decided to have a competition with two different variants of vehicle routing problems. So purely static, or let's say classic vehicle routing problem with time windows, but then also this dynamic variant where new orders would come in over the day, which means that you need to anticipate as well for some uncertainty. And so this competition was organized by quite some people actually. So you see their names here. And it is a follow-up of a number of previous challenges. So at Ortec in the past, we have organized the Verilog solver challenges. So the Verilog is a work group of the Euro, and these were like more practical vehicle routing challenges. But then also last year there were different routing challenges. So there was the AI for TSP competition, which was really on like machine learning oriented TSP solving. And there was the Dymax VRP implementation challenge, which considered a number of different vehicle routing problems. And this competition is actually organized by organizers of all these different competitions together, let's say as a follow-up on these competitions, to join efforts and to keep a bit of the momentum. And as I already explained, the goal was to really bring together these researchers from different backgrounds. And we really want to set a bar for, let's say, pushing the state of the art in solving these type of problems. And therefore also we try to provide like really competitive or strong baselines, let's say, and also a lot of you built on this baseline. And so if you wonder like why in the first place, of course, is because logistics optimizations of vehicle routing, it's extremely important, right? Like if you look at the number of trucks that drive on the road, then if we can just improve the efficiency of how we route them, then this will save time and cost and environmental impact. And this is really, even if you make like very small improvements, this can be quite a lot simply due to scale. And so, as I said before, this vehicle routing problems, they are studied in like different communities. So in the operations research community, also in the machine learning community. And what you see is that actually people from operations research also realize that it may be interesting to start using machine learning, but often these are like relatively simple or like small models, you could say, but not really like the big deep learning models that we see in the machine learning community. And on the other hand, in the machine learning community, there's also quite a lot of research being done on like machine learning for vehicle routing problems, but still it is not yet able to outperform, let's say, state-of-the-art pure OR techniques. And often like a fair comparison, let's say, to really like state-of-the-art approaches is lacking. And so this is why we decided that at this competition, we really want to bridge this gap, right? And it's kind of nice that it was started, actually, it was kicked off at the Euro conference, which is like a premier OR conference, and now it's finished as part of the NeurIPS conference, which is really like the top machine learning conference. And so not only that we like bring these people together at this different conference, but we have like the organizers, but also the participants from both communities. But we also wanted to like improve the real world impact, let's say, by having real data. So this is real data that came from one of Vortex customers. And we provided, let's say, this state of the art baseline. And we wanted to explicitly actually encourage, but not enforce participants to use machine learning based approaches. And to do so, we decided to like provide a GPU, which is often useful if you use machine learning, but more difficult to use for like classic approaches, and to have this dynamic variant where we thought would be interesting to see like the difference between OR-based approaches and machine learning-based approaches, which may be a bit more suitable for this type of dynamic problems. And so there was this competition website, which I'm sure you've seen quite a lot. I heard people like refreshing the leaderboard quite often. And so, well, the timeline, this slide is still in here, but it's not really relevant for now. We're at the end of the competition. Okay, so some statistics that you may be interested in. So we had like 150 people registered, or 150 teams actually registered, which I think was amazing number. In the end, it was quite challenging, I think, for many teams. So we had 50 teams which submitted, which I think is still quite significantly more than we expected, and a really nice result. And overall, you made like 800 submissions together, and there were 180 people in the Slack, which I think you used it also to communicate amongst your teams, because there were like 4,500 messages that have been sent. Okay, so I'm just going to quickly go over the problem, but of course you are maybe like even more familiar than me at this point. So it was like a vehicle routing problem with like limited vehicle capacities, and then time windows in which customers need to be served. And the objective, this was following the convention that was used in the Dymax challenge, is to minimize the driving time only. So there was no objective of minimizing vehicles or like wait time. And so this was for the static variant, and then there was also this dynamic variant where there should be an animation. Yeah, you can see it. So like new orders came in during the day, and you had to decide, well, whether you would immediately deliver them or put them in a truck, let's say, or whether you could still postpone the order, because maybe there would be better opportunities for combining them in routes later during the time horizon. And so, well, this is for if the animation doesn't work, a nice way to indicate how you had to interact with this environment in multiple epochs. Maybe in hindsight, epoch in machine learning terms was not the best term to use, but at least there were multiple phases or periods, let's say, in this optimization problem. And then we had different instances. So the instances were between 200 and like 700 customers, and we had like different distributions of like demand and the time windows. And as you can see, this is like not the typical maybe scientific benchmark. And the driving times were actually based on like real world road driving times. Of course, this data was anonymized, but like this driving times, they were like real data. Okay, and so then to help you get started, we had this quick start on GitHub where we provided data. So we had like 250 instances, I think, which you could use to develop your method via the environment. And then we had some baselines, and some baselines were actually added a bit later. I'm sorry that it took some time, but I hope in the end this has been useful to you. And there were also some tools and well, instructions on how to submit this on the CodaLab platform. And so this baseline, so this is a bit for if there are like also people who didn't participate maybe in the challenge, because this workshop is open to everyone participating in NeurIPS. So the baseline was hybrid genetic search, and this is basically the one slide explanation. So how hybrid genetic search for the vehicle routing problem with time windows works, that we have a pool of different solutions, right? And we have some initialization strategy, and in this pool we have different solutions. So there may be feasible and there may be infeasible solutions, and this is really key aspect of the algorithm, that we have infeasible solutions as well. By the way, this was originally developed by Thibaut, who will give a talk in a bit as well. So I hope I won't cut like too much of your material here. But anyway, the way this works is that we take like 4 solutions from this pool, and so we pair them up in 2 pairs, and we let them play what we call a binary tournament. So basically, the solutions are fighting for like who gets to reproduce, and so we take into account the quality and the diversity of the solutions, and then based on that we select one of these 2 solutions and they combine, right? And this can be like 2 infeasible solutions, can be feasible and infeasible, or like 2 feasible solutions. Doesn't really matter, right? We're open-minded, but they are going to do what I like to call the dance of romance, and then we get new solutions, and these solutions are then improved using a local search, right? Until we get like full-grown, like locally optimal solutions, you could say, which then go back into the pool. May take some time. There it is. And this, well, like 50% of the time, I think in the baseline implementation, we also use some repair phase. So if the solution is infeasible, we try to increase the weights of the penalties, and we try to make a feasible solution, which then also gets back into the pool, and we get like more and more solution. And at a certain point, we're just gonna make a selection out of that, which becomes a new generation in this genetic algorithm. Okay, and so this was actually what we used in the Dymax implementation challenge, and this was the winning entry for that challenge. And so we thought it would be nice to provide them this as open source software to start with for this next competition, to really see like, can we still further improve on this. And so I thought it would be nice to, let's say, encourage a bit of competition by having this real-time leaderboard. So that's why we had this submission platform where you could submit your code. And to be honest, this was maybe, this didn't go as smooth as that we hoped for, that we expected. There were like a lot of instabilities with the system, but we tried to make it work for you as good as possible. But this needed for us also a bit of engineering and some workarounds to make this all work. So we had like GPU workers on a cluster, and to make this all run, we had to do a lot of special things. But in the end, I think it sort of worked reasonably well for you. And so you had like a test phase where you could test whether everything was technically working, and then like in the qualification phase, you could make 1 submission per day, just to limit, let's say, trying indefinitely many submissions, and because we have like finite resources. But then we logged actually this leaderboard on an hourly basis, and this means that we can make very nice graphs showing like how the competition went. And so we can see that we sort of got a nice like linear increase of the number of participants over like the total duration that the leaderboard was open, and we can really see like how the different approaches, so the thicker ones, they are like the finalists, how they did over time. So for example, we see like a big jump here. Well, I think it's nice to see like because we had some competition also during the competition as well. And so this leaderboard on the final date, right, it resulted in our top 10 participants, which were the finalists, and we have evaluated your solvers like on new, actually, and a larger data set of hidden test instances. And to make the graph maybe a bit more clear, this is like the weekly variant, and based on the weekly leaderboard position, we also had leaderboard prizes. And so I can already announce that, because it was actually not secret, right? You knew by yourself when you like had the different positions. And so these are the different leaderboard prizes. So every time someone got like first place for a week, you got like 50 euros, second place 30 euros, and third place 20 euros. And this added up to these amounts. And unfortunately, for like practical reasons, we had to do a cutoff. I think this was in the rules. So these 5 teams, they will get their prizes because they're over 100 euros in total. So congratulations for like well, participating early and doing well on the leaderboard. It's also quite interesting to see that if we look at the dynamic problem, so this was, let's say, the cost for the dynamic problem, then here we have the baseline, basically the greedy baseline, which was like the strongest baseline that we provided, and we see that quite soon actually people were able to significantly improve, but then more towards the end of the competition, still like significant improvements were made, up to like 10% improvement over the baseline, which I think is quite nice of a result. Then for the static variant, I think in terms of like absolute numbers, there was much less room for improvement, right? And maybe in hindsight, we should have looked into like getting bigger instances, which would have, I think, left more room for improvement. But definitely there was room for improvement, right? As we can see, like many of you still improved over the baseline. There was some noise, but you know, you could submit your solver more often. So on average, we really saw that yeah, also the quality of the solutions was improved over time. And so that brings us now to the finals, right, where we have evaluated this top 10 solvers on actually 100 new instances, which came from the same distribution, but we used 2 times longer run times. And well, so these slides aren't adapted for today, but they are, the results will be announced today, as well as the prizes. And so this slide I will skip. So that brings me to the end of the introduction. And now I would like to head over to Thibaut for the keynote. So, Thibaut, can you maybe join in? Laura,
yes, absolutely. Can you hear me?
Yes, I can hear you.
Excellent. I'm just going to set up my slides here, put them on the screen, and we are ready to go.
Yes.
So
Sharing. I'll stop sharing.
Yes, no problem. Okay. Good then. Okay, good.
So by the way, one thing I forgot to mention still is like this meeting is being recorded. So if you don't like to be recorded, please turn off your camera or don't like interact. Sorry if it's too late. If you have objections, like reach out to me and we will find a solution.
Okay.
Okay.
Sounds good. Can you all see my screen properly?
Yes.
Okay, fantastic. So, well, I didn't want to create something extremely complex for this keynote. I just wanted to make a very short historical tour of some of the methods that we have been using in this challenge, especially the heuristics, and discussing a bit the pathways, current research paths in the vehicle routing literature. For everyone who is here, some of you are like more from the ML community, so it's more a kind of rejoiner, such that we all know a bit more of the history of this field. So very often we see the vehicle routing problem from the lenses of a quite stylized problem, because let's say the most canonical and classical problem in this family is the capacitated vehicle routing problem. So you know this problem well. You have requests that are located on a map, or you are given a distance matrix, and your goal is to visit those customers to deliver the product that they want, and minimize the total distance. Of course, you cannot make a single tour, which would be optimal for a TSP, because your vehicles are limited in terms of their capacity. Therefore, you have to make sure that in each route, the capacity of the truck is not exceeded by the total demand of the customers. It's a very classic NP-hard problem. It is very hard to solve still for exact algorithms. So if you look at the world of combinatorial optimization, there is NP-hard and NP-hard. I mean, some problems like traveling salesman can be solved super well for very large instances, like 10,000 points can be solved using Concord. For the VIP, even the most simple variant like the CVIP, like this one, the best exact method that we have in the literature they cannot really reliably solve problems of more than like 200 customers. And even then, it can be quite unstable. It can take days for some instances that are badly structured. So if you look at practice, most companies are unable to apply exact solvers for vehicle routing application because it's just too time consuming or too unstable. That's why there has been a lot of work on heuristic solution methods that are designed to be fast and efficient. The second curse of vehicle routing problems is the viability of the practical applications. You find routing problems everywhere in many, many application areas, and all these areas have their own specific requirements. So I have put a very small photo here that I think illustrate one of the many things that can happen. It comes from an application where you have to actually deliver new cars, and you have to make sure that every time you make a route, the car can actually fit on the trailer. So even inside the routing problem, you may have a very complex positioning or packing problem just to validate that there is a certain configuration of your trailer that can carry your cars, your goods in the occurrence here. But you find so many things. You find different objectives for different applications, like profitability, fairness, level of service for the customers, consistency in the deliveries. You want to see the same driver every day. Simplicity in the geographical distribution of the solution, like compact solutions that are easy to represent. You have problems that are integrated with other decisions, like playing over an extended planning horizon, multiple periods. You can have many depots. You can have a mix of different delivery vehicles with different characteristics. You can have synchronization issues, for example, two workers meeting at the same point to do some intervention. You have also a lot of fine-grained characteristics of demand or the network or the vehicle, like time windows. You have seen time windows in the problem of the challenge, like every customer has to be delivered in a certain interval of time. You can have like loading constraints, skills, congestion taken into account, electric vehicle with charging station. I mean, you can basically work on routing during an entire lifetime. And well, some of us do that. Actually, this is a field that has like received hundreds or thousands of contributions over more than 50 years. So if you look at routing in a very high level view, you can always think as a problem of grouping deliveries together into different resources, for example, vehicles, choosing the sequence of the deliveries and evaluating that sequence. So if you relate to your problem, the VIP with time windows, you had the grouping, which is like which customer go together. The sequencing was the order that you choose, and the evaluation was just verifying that the time windows were met correctly. And you can often distribute many of the characteristics of the problem along these three main tasks. You can see which characteristic of the problem impact which aspect of your solution method, and that helps a lot to get a full picture of how to deal with them. I like to say that vehicle routing is a kind of double combinatorial explosion because it's inherently combinatorial because it has many possible permutation and combination of visits. But it's also a combinatorial explosion due to the problem characteristics. So if you look at the number of characteristics of problem we know in the literature, it's perhaps 200 or even more. In practice, you don't only find these attributes in isolation. You often find them combined together. So up to 2010 and something, there were so many papers dealing with specific problems that it became a trend that it could be possible to design 200 papers dealing with all these combinations because there were just too many, and most research was unable to come up with a general algorithm that would work well for all of them. If you look a bit at this, you can say that the challenge at the time was to get unified solution concepts and methods. In machine learning, people would say that they want algorithms that can generalize well along a very large set of data and problems. A bit of history tour. So in the 1960s to 80s, most methods were actually construction based. So you would construct a solution piece by piece, for example, by merging roots, like in the clap and write algorithm, until you get a complete solution on stop. It has been successful. It is still used in some applications sometimes. And if you look at the vehicle routing problem just with capacity constraint, you can expect like, let's say 15% error gap when you do something like that, okay? But it's extremely fast. So you can apply the construction techniques and use it, for example, for initialization because it's very easy to design and very fast. You have different flavors of construction techniques. The one I explained, the first one on this slide is what we call the savings method, where you are going to initially start every customer visited by a single vehicle, and then you merge these two together in the way to maximize the savings when you do that, okay? So it's very greedy. There has been an algorithm that was called sweep algorithm, where you kind of look in a circular fashion around the depot and collect customer visit as long as it fits, and then you start a new route if the capacity is not enough. And you have also methods that were designed on first solving a traveling salesman problem, like a giant tour that visit everyone and then cutting that into pieces. So that's really, really early work on the vehicle routing. These were like different construction techniques to start to initialize a solution and get something to work with. After that, let's say a little bit after, local search started to be quite a big thing, and people design efficient local searches for vehicle routing problems. So a local search, as you have certainly seen in the startup code and played with, is just a way to move in a search space from a current solution and trying to improve it by doing small changes. So typically, you can see it as moving in a graph of all possible solutions, and the move that allow you to change the solution, define how you can move along this graph, and your search strategy will tell you how you navigate in that big graph. There is many different flavors of local searches for the vehicle routing problem, depending on the type of move that are used, the type of neighborhood exploration that is designed, and so on. But it's typically a method that delivers for you solution around like less than 10% error gap. And if you repeat it from different starting points, you can get a little better. So I have marked like roughly 4 to 8% error gap using pure vanilla local search on the CVIP, for example. You have many neighborhoods that can be used. A simple terminology is to count the number of edges that you change when you do a move. So for example, if you do 2-opt, you are basically breaking 2 edges, reinserting 2 new, and that is a very simple move that kind of uncrosses bad delivery sequences, for example. And there is many other neighborhoods. For example, all-opt is a neighborhood that consists in relocating a sequence of visits to a different location in the solution. And it's actually a special case of 3-opt because it breaks 3 edges and put them back in a different fashion. You can use relocate. That is a very important neighborhood in many methods. It just relocates the delivery to a different place. You can swap 2 deliveries. And you can do stuff that is a bit more complex, like, for example, exchanging 3 deliveries versus 2 is what we call a cross exchange, and so on. On 2-opt star, for example, will exchange the tails of 2 different routes. So these are many ways of enumerating changes that can lead to solution improvement. And all these neighborhoods have the common characteristic that they can be evaluated usually in less than quadratic time. Beside that, you have larger scale neighborhoods that are designed to explore neighborhoods that could be potentially very large. For example, Link Cunningham, that is the early version behind the LKH3 algorithm, consists in a very clever enumeration of higher order move that can go up to 5-opt. So they use some very clever pruning techniques to enumerate up to 5-up move and find improving move in that space. That's something very interesting and very challenging to design. So here we really come into the realm of complexity issues and algorithmic design of efficient way to search larger neighborhood. Okay. For people liking machine learning here, you can even use pattern mining in some sense to try to identify useful high order move that can improve your search. When you do local search, very often, even a quadratic size neighborhood is going to be a bottleneck in your method. So if you look at modern meta-heuristic, very often on larger problems, with let's say 500, 1000 deliveries, it's already important to not search in quadratic time because it's too slow. So one way of restricting neighborhoods is to impose restriction about which customer you can swap or in which position you can relocate a customer. So this has been known as granular search. You basically only look at swap or relocate between positions that are close enough or related enough somehow. Okay. You can also see it from the lenses of the graph saying, I only test move that create at least one short edge. So that's really useful. There has been some trials, tentative to use learning to actually restrict neighborhoods. And I've personally also played with that. I've not been so successful so far and didn't find something that would be better, for example, than just classic ad hoc geographical restriction. For example, I tried Walter the heat maps, but I was not successful with that when doing it in a granular search context. Perhaps somebody else can come up with a better idea on that than me. Another stuff that is very fun is sequential search. Sequential search comes from a very simple observation, is that if you look at a move and you decompose it, it breaks some edge and it inserts new one. So you can see it as a sequence of addition of deletions. If you want this move to be improving, you need the total sum of this addition and deletion to improve your objective. So the total cost of this operation must be negative. And if the total cost is negative, that means there is an order for performing these addition and deletions for which every partial sum is negative. And this is the basic principle of sequential search. It prunes the search by imposing that every partial sum of actions remains negative over the exploration of the move. It can be very powerful, and that's actually one of the principles of the link-adding heuristic as well. Okay, well, local search is great. You can play during months doing efficient coding of local searches on one of the main factors of success of the hybrid genetic search that you have been using in the code starter is the fact that the local search is very finely tuned on design and very efficient in terms of implementation. But you can always do better for sure. But local search will ultimately lead you to a local minimum. This is why there has been a lot of effort in the OR literature to escape from these local minima and get better solutions. So to do so, we use search principles that are broadly defined as meta-heuristics. Meta-heuristics are just general principles that attempt to escape local minima in different ways. We can divide those into two main streams: meta-heuristics that improve individual solutions, and meta-heuristics that work on a population of solutions. So I'm going to show some examples. I apologize in advance for those who I could not put in the slides because we have very little time and there's so many noteworthy meta-heuristics in the vehicle routing literature. So the first meta-heuristic I wanted to highlight is the unified taboo search. It existed more than 20 years ago, and it was actually very efficient. If you run a modern implementation of UTS, of the unified taboo search, you get solution quality of around 1% error gap. So it's a 20 years ago method that is already, let's say, 1%, 2% from the best known solution if you apply it today. It has very simple principle. It always applies the best relocate move in the entire neighborhood. and it used taboo memories to avoid cycling. So if you move a visit from route R1 to R2, you cannot insert this visit back into the route R1 for a certain number of iterations. Super simple. But it also has additional strategies. For example, they gradually penalize characteristics of solutions that are frequently found in the objective function in a way to lead the search towards different regions of the search space. And it also penalizes infeasible solution. You can have infeasible solution, but they receive a penalty. I'm going even earlier, 1995, Rochan Taya. Rochan Taya, I think they have understood everything 30 years before all of us, because they were doing most of the main principles that are successful nowadays. They were designing a taboo search, which was using this time 2 types of moves, swap and relocate. To avoid searching the entire neighborhood, they was doing a probabilistic selection of moves. So at every phase, they would only select a subset to try. So they gain time and also gain in terms of search diversity. And they were already doing some form of mining in the solution. They were detecting good fragments of solution that appear often. They were keeping them in a pool. And based on that, they were trying to rebuild new solutions using a mathematical programming model. They were also applying decomposition phases. So if you look at many methods recently developed on machine learning, like learn to decompose and so on, well, they were doing that in a ad hoc fashion, but it was already very powerful at that time. And they were already solving exactly some TSPs when I pumped regularly just to get additional performance. Now, let's jump a bit in time. 2007, ALNS from Pisik and Ropker. ALNS turned into a very, very successful solution method for many vehicle routing variants due to its simplicity of concept. The idea is to apply the read and recreate principle. You take a part of the solution and you try to rebuild it in a better way. And in early work on read and recreate, for example, papers by Shao or Shrimp et al. 2000, they were very they asked for very high quality reconstruction. So they would spend a lot of time reconstructing using, for example, exact formulation and doing it a few times. When Pisik and Hopker designed their read and recreate, they decided to go totally against that. They would do very, very fast on numerous reconstruction, but in a way that was heuristic. And they would do that in different fashion with different operators. For example, you would have different ways to deconstruct solutions and focus on a sub-problem, on different ways to reconstruct them. On this diversity, on quick execution would contribute to the success of the method just by sheer repetition and tentative. And it has led to very good solutions. And there is modern implementation of ALNS that are very competitive with recent meta-heuristic for the CVIP, for example. There is also some iterated local searches that has been developed and that are quite efficient. I will perhaps pass a bit fast to not spend too much time. Some guided local searches where you will iteratively detect some bad edges in the solution. So the idea is that you want to characterize what is bad in a solution. In the work of Arnold and Sorensen, this characterization was a bit offline. There was a prior study of what features are good or bad in solution, and they were using the result of that study. But it could be seen in also designed in a more online fashion using learning. And they were using very, very sophisticated neighborhood searches in that work. One paper I especially like also is the Caesar paper from Christiansen and Vandenbergen. Their idea was to revisit again the read and recreate principle of Pisik and Hopker, except that they trimmed most of the component of it. They said, well, ALNS of Pisik and Hopker, it was using a lot of read and recreate operators. It's very complex to implement, complex to explain. Let's see how much diversity of operator is important. Let's just take a single operator of deconstruction, a single operator of reconstruction. Let's put no adaptation in the way we select operator and let's see how it goes. And actually they made something extremely good using very well-designed read and recreate operators. There is this idea that when you read a solution, you need to create special slack. That is, you need to remove customer visits that are close enough such that you can reconnect in a very different way, possibly. So you need to create that space when you destroy your solution. You don't want to destroy randomly. And it had a very good performance on many problems. So now I'm connecting to the second stream of meta heuristics, which are very close to what you have used in the challenge. Okay, so those are more population-based methods. And I think all these methods, they take their roots from one paper, especially, and it's the paper of Christian Prince in 2004. You need to see the picture of that time. At that time, people were very heavy on taboo search and single trajectory meta heuristics. The consensus is that taboo search was the winning method for a very long time. And Christian Prince arrived and said, well, I have a genetic algorithm based on a population recombination that is competitive with all of you. And to do so, Christian Prince had to solve one key challenge. At that time, it was not very well known how you would recombine two vehicle routing solutions. The problem was coming from capacity constraints. If you try to work on a complete solution with the roots and you try to combine it, two solutions into one, you often break a lot of things and you end up with solutions that are either infeasible or that have a too large number of roots on which are very bad. So Christian Prince said, there is no need to actually mark the visit to the depot in the solution. Because if I look at the solution as a kind of giant tour with all visits as a big tour visiting everyone, there is a simple dynamic programming algorithm that can optimally cut this solution and reinsert the visit to the depot. And using the ability to always optimally translate a giant tour into the best solution that corresponds to this giant tour allow you to encode much more easily a solution, because then you can encode solution as giant tours. They are simply represented as permutations, and you can use all the classical crossover that are known for permutations in the genetic algorithm literature. So that makes it suddenly easy to generate new solutions through recombination. And that was really the key idea that suddenly allowed to apply genetic algorithm efficiently. And the other thing that Christian Prince did was to apply local search, because local search is essential to get good solution for vehicle routing. So you don't want random mutation to try to improve solution. You need something that is really driven by local search. And you want to keep the diversity of the population. So when we built our algorithm, more or less a decade after Christian Prince, we retained most of these strategies, but we improved a lot upon the local search. We used these neighborhood restrictions, the granular search that I explained a bit earlier. We added the ability to deal with penalized infeasible solutions and to have adaptive weight for penalties, and a specific measure of diversity that permits to retain solutions that are good and diverse. Okay. So that's what we did, and which really led to good solutions. So when you want to keep solutions that are good or diverse, one way to do that is to rank the solution by cost and by contribution to the population diversity, which is kind of distance measure to the other solutions. And when you remove solution for survival of the fittest, you will use that weighted criterion. So you will basically remove bad solution according to this criteria and keep a good mix of diverse and good solutions. What we also did at that time was to attack the issues of all these problems. I told you it was possible to write 2^200 papers because most methods were designed to a single problem. We looked from the general picture and we designed a method in a way that every problem characteristic that was brought to us could be easily included in a few steps of the method, either in the way the local search was working with the move that changed the assignment of customer to vehicles, the way the routes were evaluated, and the way we define the neighborhoods. And the idea was to keep most of the code generic and having just a few, let's say, polymorphic components dealing with the different problem characteristics. You can have a general sketch of that. I will not spend too much time on this, but the funny thing is that suddenly we could have a very different view about the challenges of vehicle routing problem at that time. We were bringing in the game a single algorithm that was generic, and we took 50 different problem variants with different constraints and characteristics and over 2,000 benchmark instances. And for all of these problem variants, we look at what was the best algorithm specialized to this problem in the literature and compare to it. And what happened is that with a generic method, we could obtain state-of-the-art on all the problems. So it was possible actually to generically solve efficiently VLP with capacity constraint, duration, backhauls, asymmetric costs. This long list of things I put just for fun, just to show that all the list of problems that can be efficiently dealt with. And well, it was not only generic, it was also the best for all these methods at that time. And even nowadays, it remains a very, very difficult challenger for many variants. We still hold many of the SOTA results for many of these variants. Okay, at that time, we were presenting table like that, table and tables of results where we compare with one algorithm, another algorithm, which are the top for this variant, and then show our results in terms of error gap to the best known solution. Okay. The big issue was that sharing a code like UIGS was just impossible. As a community, it's impossible to maintain a code for 50 variants. You have people that come and tell you, hey, I have this variant that I'm dealing with, it's not fitting in your scope. Can you extend it to work with us? Or I have different constraint objective. It would have been impossible to share it and to maintain it as a community. That's why, just like a couple of years ago, the idea came to just share the crisp implementation of that code for only the capacitated vehicle routing problem. Why we do that is because it would be extremely simple. You could just like print it on 20 pages, read it. Within 2 hours, you would know the entire code. And then it was easily extensible. Somebody could learn about the code and specialize it to its own problem. The goal was to really find a good trade-off between conceptual simplicity and performance. So it has been quite a successful exercise because we put that code last year in GitHub. Many people have forked the code, contributed to the code. We had great contribution, for example, from Changyun Kwong, who did very nice Python, Julia, and C APIs. More recently, Niels, in the context of the challenge, did very nice Python APIs that allow to call to the different subcomponents of the algorithm. It still holds the state-of-the-art result for the CVIP, and it's continually improving. And notably, the method that has been provided as starter code for this challenge is an adaptation of the CVIP code to the vehicle routing problem with time windows. On Wouter already explained that it was extremely successful in the Diamax challenge, and with very good code optimization, data structures, a few additional tricks, it was a very, very good method for this variant. So current state of research, just to discuss a bit where all of this is going. There is still research on heuristic for vehicle routing. The thing is, if you look at the classical variants, the current OR-based methods are extremely close to the optimal solution or the best known solution. Like the gap are extremely tiny. We are talking of 0.1, 0.2% on average usually. It's still a very good testing ground because there has been a long tradition of benchmarking. People have been using the same instances during a lot of time. So it's a very, very good testing ground for new search strategies. In the paper of the AGS CVIP, the one published in 2022, we made very nice benchmarking of recent methods on a single machine using the Ushuaï et al. Instances. looking at how they converge in terms of error gap over the runtime of the algorithm. So basically, every algorithm was run up to a certain time limit, which is 4 minutes for every 100 customers. So you can see the progress from 1 to 100% of that time limit. We do a time limit that is dependent on the problem size because the Ushuaïa instances are from 100 to 1,000 customers, and the 1,000 customers are much harder than the 101, so they need a bit more time. And if you look at the final result at the termination, like for example, the AGS CVAP, that is the open source code, it's really like 0.1%. But you have two other methods at least that are very close to that. Like if you look at the old AGS was still good, and Philo is a very nice method. It's here. You have also, I think, the Caesar method that is a square, which converge a bit later, but which has very good solution at the end. So there's not a single method that provides 0.2% result. There is quite a few methods that are able to do that nowadays, and they are fairly different, which is very interesting. And we have seen that in the DIMAX challenge. Some of the winning methods were actually hybrids of these approaches. Now, if we look at the ML literature, one thing that was a little unfortunate in the beginning is that a few early ML papers did not really use SOTA algorithm as a benchmark. We saw, for example, OR tools that has been used quite a few times in the ML literature as a comparison, or even Lin-Cunningham tree to a lesser extent. For this reason, we have put OR tools in this analysis. It's really far away from the state of the art. Okay, so even taboo search from 20 years ago actually still performs better than OR tools. I don't want to create a criticism of the OR tools. It's a fantastic tool because it's very generic and simple to use. But in terms of sheer performance on a crisp variant like the CVAP, it is not the recommended comparison for an academic study, I would say. So it's good for practical application, but I would not use that for benchmarking on trying to improve upon the state of the art. So my recommendation is, as we progress and unify a bit the research between two different communities, the OR community and machine learning, it's important that we both are aware of the respective improvement on both communities and strive to use common benchmarks. We need to build upon the best known methods or compare with them. Otherwise, we are just like running into loops with research. We do improvement of methods, then deterioration, and then we improve again, and so on. Never going to converge. There is a nice website that you can refer to if you want to check for benchmark instances. Is this one, the CVAP Lib. For the CVAP, the Ushuaïa et al. Instances are still very popular and challenging. I think there is still very good interest in working with them. And I have seen a recent tentative to develop a standardized benchmark for learning, because Ushuaïa just has 100 instances. It's not a large domain to learn. It's not enough. So the same authors with the Quiroga generated 10,000 instances from the same distribution, and were able actually to produce non-optimum for every solution. So if you want, for example, to train with non-optimum, we have a list of instances and solutions that are all optimal. And it's not an easy thing to actually solve 10,000 instances with 100 customers to prove an optimality. It's very difficult and very useful. And you also have a generator if you want to generate more instances from the same distribution. So I think this can help a bit for future benchmarking. You can always put more components in the mix to improve performance. The problem is that you get more and more complex. You can add a little strategy, one more neighborhood, one more thing. You shave one small fraction of a %, and you get a little better. But I think as scientists, we need to understand what is the relative strengths of what we put in the method. Do ablation analysis, understand what is the relative contribution of each component. Especially with machine learning component, if you put some learning inside some heuristic, for example, you absolutely need to make the effort to make a non-learning version of it. For example, just with random choices or very ad hoc rules that highlights what is the real contribution of the learning component. We see also recent studies towards larger scale instances, and I put some reference here. And there is still many problem variants of importance that are super hard. For example, when you have interaction, synchronization between routes, these are very difficult variants. If you integrate routing with strategic decisions on inventory, location, districting, this is very hard. If you look at the user side or competition, you have extremely challenging domain of applications there. And also all the dynamic and stochastic problems. You have tasted a bit of them in the challenge. Now, it was one problem in the dynamic family, and it was really, really challenging. So that's why we decided in the challenge to do something that would be canonical, relevant for practice, and difficult. Yes?
Can you hear me? Can you try to wrap up in favor of the schedule? I think we're a bit over time, which is fine, but now it's good to wrap up.
Yeah, then I will not discuss why we designed this variant. I think you all understood why. It's very challenging, and that's why we decided to go with that one. I've not decided to discuss too much the dynamic policy because you guys are the one who made tremendous effort to design super nice dynamic policy for this problem. And I wanted to thank you, Wouter, for designing this challenge, putting all the energy into this competition, the benchmarking, the evaluation. That was truly amazing. You carried a huge weight on your shoulder and did a tremendous job. So thanks a lot for the attention. I'm really looking forward to learning about all the methods that you have designed and on the successful strategies.
Okay, so thanks a lot, Thibaut. I think that's a very nice historical overview, let's say, and a bit of like future perspectives. And I think it would be nice if we can have some discussions maybe later today, because I see a lot of opportunities, also like a lot of heuristics still inside the methods, let's say. So I think also a lot of opportunities for using machine learning potentially, where you've like indicated some already. So we're a bit behind on schedule. We also started a bit later, so sorry for that. But I propose we will be back at 15:10 or like 10 over the hour, let's say, in your local time zone. I think so. 8 minutes, 7 minutes from now, and then we will start with the presentation by, let me check, Roberto Hood and the Berryman. So grab a coffee and be prepared.
Okay, great to have some coffee time.
Hello, hello, hello.
Yeah, so Laurens, I think you're host still. Can you allow Florentin to share his screen? Someone?
Let's see. Yeah, I think
That looks like you're able to do it. Okay, so welcome back everyone. It was a very quick break, but I hope you enjoyed it nonetheless. So now we will have 6 presentations actually by the finalists, which are in sort of random order. Afterwards we will have another break. So it should be 15 minutes, so we have like 5 minutes per team, and then with a few minutes for questions. And so I would like to give the floor to Florentin from Team Alberto Hood and the Berryman.
Thank you a lot. So in this talk, I will present our solution approach for the dynamic variant of the competition. We submitted a 2-stage set petitioning approach, and our team is called Alberto Hood and the Berryman, consisting of Roberto, Barrett, Marlene, and me. So in this talk, as I said, we only focus on the dynamic problem. And in the dynamic problem, we basically have 2 decisions to make. The first decision is a set petitioning decision to decide which customers to postpone and which customers to serve now. And the postponed customers just transition to the next decision point, while for the serve now customers, we have to solve the capacitated vehicle routing problem with time windows. And as the routes can't be changed later on, this part is static. And so we just used Thibaut's solver for this one and didn't address this part. So we only look at the set petitioning problem in this talk. And in an ideal world, you could do the set petitioning problem given all future requests by just solving a capacitated vehicle routing problem with time windows and release times. And a solution to this problem would not only give us the respective sets when to serve which customer, but also the routes as well. But we are not in an ideal world, and so a forecast must suffice. And so what we did is we approximated the future by just sampling scenarios. In this example, we sampled 3 scenarios. And in our first approach, which we did in the beginning of the competition, we solved a multi-scenario approach. So basically, we took the current request, glued them to a request scenario, solved for this problem as a capacitated vehicle routing problem with time windows and release times. We did this for every scenario, and then we tried to find a consensus solution. And this worked well to some extent, but we thought maybe we can improve on this by looking at this problem more holistically. And so in our second approach, which was our final submission, we looked at all scenarios together. So what we did is, again, we sampled scenarios, and then we included 2 more rules. And the rules are that customers that are served, or one of the current customers that are served now in one scenario have to be served now in all scenarios, and the postponed customers in one scenario have also to be postponed in all scenarios. And then we minimized over the cost of the current routes plus the mean cost over all scenarios. And for this, we include decision variables. XR means the current route R is implemented, and YRI means that the future route R is implemented in scenario I. And so in total, we obtained the following mixed integer linear programming model. So we try to minimize the costs of the current routes plus the average cost over the routes, all future routes in all scenarios, such that each current customer is served, and the sampled customers are also served in each scenario. And following from this constraint, also we have that if a customer is served now, it is served now in every scenario. And this posed some challenges solving this mixed integer linear programming formulation, because of course we have a combinatorial number of decision variables, because we have a decision variable for each route and each feasible route in each scenario. And we addressed this by implementing a column generation approach, but still pricing out routes in this column generation approach is NP hard. And so we addressed this by relaxing the elementary constraints of the routes, and we instead generate QT routes. So the routes still adhere to capacity constraints and time window constraints and release time constraints, but do not fulfill the elementary constraints anymore. So what do we get? We don't get a feasible routing solution to the entire problem, but we get dual bounds on the marginal costs of serving a customer now versus serving the customer in the future. And based on these costs, we can then partition the set of current customers. And once we have the current customers that we want to serve now, we can just use Thibaut Vidal's algorithm to route these customers. This concludes my talk. I really want to thank the organizers for making this competition very accessible and for your extremely fast responses. And I had a lot of fun, and I think otherwise I wouldn't have participated in my free time. And if you have any questions, or if you want to check out our code, it's not uploaded yet, please reach out.
Okay, thanks a lot for Tim. Very nice presentation, very elegant method, I would say. So are there any questions? Yeah, it's allowed to clap. Is there someone in the audience maybe who would like to ask a question? No one? Oh, then it turns out I have a question, because I was wondering, like, how many scenarios do you consider if you do this scenario sampling?
Due to the very limited time, we only use 2 scenarios.
2 scenarios, okay. Yeah, because that was my question. If you solve it like all in once, I can imagine that very challenging problem to solve.
And a follow-up to that, what percentage of the 60-second window was spent in evaluating those 2?
2/3. So 2/3 for solving the scenario, and then 1/3 for actually routing the customers in the end.
Thanks.
Okay. And can you, because you said these QT routes, I missed that part, like they satisfy like the time and demand, but what is the constraint that is not satisfied, let's say?
So elementarity constraints, so customers are allowed to be served multiple times.
Okay.
It's not necessarily a cyclic route. Yeah, and these routes can be constructed in pseudo polynomial time, but yeah, they're not feasible routes.
Okay. Okay, so thanks a lot. Then I think we will move on to the next team. So you can stop your screen sharing. And I think Niels is presenting, right, from OptiML. Can you share your screen or do you need to write still for that? Yes. So take the floor.
I think you can see my screen now.
Yes.
Okay, yeah, so I'm presenting for Optimal, Jasper, Leon, Luke, and I. And we had quite a bit of a different approach to this than the previous team, but you'll see that in a minute. So due to the limited amount of time, I'm only going to talk about what we did for the static solver very briefly. But as a high-level overview, we took the given baseline, as many other teams did as well, and simplified it quite a bit. As some highlights, we removed the giant tool representation, the split algorithm, the constructive heuristics at the start, a whole bunch of things, which almost half the number of parameters that our static solver has compared to the baseline, which was very useful when we got to the tuning at the end, because there was a lot less work to do. We also tweaked the local search a bit, but none of that is very, very radical. It's just making it a little bit faster, implementing it all slightly differently, but it's very much based on the baseline we got there. A few other things as well that we mentioned in the short summary paper that we don't have time to go into today. So I'm skipping the next 2 slides, which basically explain in more detail what I said just yet, to get to the main event, which is our dynamic solver. And there, our main idea was that we already know the data generating process here. We have a lot of distributional information from the static instance that we're trying to solve, and we can use that to simulate ahead future epochs and get simulated requests and use that information to basically solve a simulated hindsight problem in a sense. And based on frequency information that we get out of all those simulations, we can then decide which requests to dispatch now and which requests to postpone for later epochs. This is probably easiest to explain via an example, so that's what we're going to go through in the next few slides. So here you see an epoch instance. There's one must dispatch request that is tied in this epoch that must be dispatched now, and there are 10 dots around that are optional requests that we can dispatch now. We can also postpone. And the question now is, which of these do we want to postpone, and which of these do we want to route now together with that must dispatch request? And now, as a simulated instance, we just simulate a number of requests from the static instance that you see pop up around these various dots. They're the smaller dots that are visible, hopefully, on your screen as well. And then each of these requests has a non-zero release date, so they cannot be paired with the must dispatch request. And the idea is that with this extra information, we can then solve the simulated instance, which gives us a lot of different routes of these optional requests that can be paired with any of the requests, but the must dispatch request can only be paired with the existing requests that are already in the set. So here you see one route highlighted in red that contains the must dispatch request. This is just one solution. We solved this very quickly in less than half a second, which gives us a reasonably okay solution. It's not perfect, but it's good enough to get some information out. And this is just one simulation. And of course, we do this a lot of times, about 40, each of half a second. And we just get a lot of distributional information from this about how often an optional request is postponed or not. We summarize that by frequency. And basically, we get the frequency of postponement for each of these optional requests. And then we use a very simple threshold, in this case, in the example, 80%, to determine whether to postpone or not. In the competition, we use different thresholds for different epochs. But here, for the example, 80%. And then based on that, we just label. You get a number of requests that are now definitely postponed, and a lot of them that are still in play. And we noticed that a single simulation cycle was not enough. Comparing to the hindsight solutions, we do not postpone enough requests in early epochs. Our solution to this was, well, it worked well the first time, do it again. But now the postponed requests cannot be paired with the must dispatch request again. because it's released, the postponed requests have a non-zero release date as well, so they can only be paired with the simulated requests. So they're pushed later, and that forces our simulations to pair the must dispatch requests with the optional requests that are still in play. We do this 3 times, and that's the parameter setting we chose, and we label all the postponed requests after each of these cycles. So here you have one more request that is postponed in the lower left. In total, in the competition, we do it 3 times. Here, I'm sticking to just this. This gives us the final dispatch instance, and this is the one we actually solve for about 20 seconds in the time limit we have. So that gets us this solution, one route that contains a must dispatch request, and another route that does not contain anything that must be dispatched. And as a final step, we do not route that particular route because we don't have to. We can also postpone that one. And I saw that a few other teams also came to that realization that you can freely postpone routes that do not have to be dispatched. We also do that. And that is more or less the solution method we came to for the dynamic problem. So very briefly, thank you for listening. That is it. And if you have any questions later, you can email me, and the code is also available online. So feel free to have a look.
Thank you, Niels. Very slick presentation in dark mode, I would say, but also very good content. So are there any questions from the audience?
Yes, I have a question.
Yeah, that's nice.
So I was wondering, so you mentioned that you had to choose a threshold, but alternatively, you also repeated this process like 3 times. Can you say something about what is the difference between the two? Why not spend more effort in trying to find the best threshold and only do the simulation once?
We did quite a bit of this. And I'm going to go back a bit. Like here, you can see the numbers, right? These numbers are like here, they're just an example, but they're fairly indicative. Some nodes are postponed almost certainly. Like we're very certain that doing them now is a bad idea. So even if you set a threshold that is very high, you would still postpone most of them, most of the ones you know for sure. It's really about the ones you're not that certain about that we don't know yet. And when you then keep all of these in play, you get basically a bit of route switching that happens, where sometimes the route goes via the left and sometimes the route goes via the right, like the red one we're looking at. So you get these nodes that are somewhat in the middle, and you need to filter them away somehow. But we don't know yet whether we should filter the left side or the right side because this switching happens. And it's very hard to have one threshold that can detect this in a very good way. This switching keeps happening. So somehow you need more information than we have after one simulation cycle. Undoubtedly, we can do this better, but we found this fairly difficult to do from just a single simulation cycle.
Thanks.
Okay, thanks. So I think there we needed to wrap it up, but I think again, very nice method based on simulated scenarios. And so the next presentation will be Team Dynamo by Mohammed. Can you share your screen? Are you here?
It's just a second.
Are you able to share your screen? Or do you need? Yes.
Yep. Hi, everybody. This is Mohammed Ghanam. I'm a first-year PhD student, and I'm going to present my method for the dynamic vehicle routing problem.
I see a black screen. Is it just me?
I do see the screen.
You can? Oh, then it's just me. Okay.
I don't know about other people.
I can also see the screen.
Yep, you can see it.
Okay. So first, what I added to the static baseline is a new crossover operator that I got from this nice paper, comparison of 8 evolutionary crossover operators for the vehicle routing problem. And it starts by choosing a random node and then checks the outgoing arcs from both parents and chooses the one with the least cost, and it repeats this process until the options that are already assigned, and in that case it chooses an unassigned node until all nodes are assigned. And for the dynamic solver, my main idea was to adapt hybrid genetic search for the dynamic variant. And the first step to do this is to allow partial solutions, meaning solutions that only visit a subset of the customers in the epoch. And to start with an initial population of partial solutions, I start by random orderings of the customers, and then delete some of the optional nodes with some probability. And for the fitness, I expanded the definition of the feasibility to penalize the missing must dispatch nodes by adding the number to the penalized cost. And for comparability, I so that different size solutions are comparable. I normalized by the number of nodes in the solution. And to allow for flexibility in the future epochs, I added the latest time of arrival for each of the nodes that appear in the solution. And this would favor the ones that end earlier in the earlier epochs. For local search, I added 3 ones that modify the customer set that is assigned. One that is called delete, that removes a customer from some route. And this one is only applied if it improves feasibility. And another is the swap out, which exchanges one of the unassigned ones and puts it in place of one of the assigned ones in the route. And this is applied if there's any improvement in the penalized cost. And after all the local search loop is done, I try to add a customer in the routes, but only if it increases the distance by a small amount. That's all I have. Thank you all for listening, and if you have any questions, please go ahead.
So thanks a lot. Are there any questions? By the way, after some seconds, I was able to see your screen, luckily. So do we have any questions for Mohammed? No questions. So I wanted to say first, like, compliment, like, I really like your pictures. Are they hand drawn, or is this some like tooling you use for that?
It's a very nice tool. It's called Excalidraw.
Okay, well, you should send that to me afterwards.
Sure.
Yeah, so I was wondering, so you have this solution where you then like allow, let's say, customers to leave out of the solution, and if I interpret it correctly, you basically optimize for the average cost in the solution. Is that correct?
Yes. Yes.
So then don't you get the effect that, let's say, customers which are more distant, let's say, which have like higher average cost, or maybe like sort of outliers, that you'll always postpone them? Is that something you've considered?
Could you repeat the question again? The internet was.
If you have customers which are a bit farther away, let's say, from other ones, then which add more to the cost on average, then you will always leave them out, basically. If you have like outliers.
Yes, that is definitely a bad thing in the method, but the alternative I tried to normalizing this way is adding something for the non-dispatched customers, but normalizing worked better.
Okay. Yeah, I can also imagine. Maybe, I'm not sure if it's not what you want, right? If it's like very much an outlier, then maybe it's good to postpone because maybe you get another request nearby. But I think it's interesting that you have this effect. Okay, so any other questions? I think otherwise we can move on to the next presentation, which will be Team SB by Yonghae. Can you share your screen?
Yep. Can you hear me?
Yes.
Good.
At least I can. Not sure if the rest can. Probably.
Okay, so hi everyone. We are Team SB, collaboration of Samsung SDS and Bielefeld University. So I am going to present two main ideas, one for static problems and one for dynamic problems. So basically we just, for static problems, we basically use the original HGS, but with one modification, which was on the binary tournament selection part. So I'm sure all of you knows this figure, and the binary tournament selection part is here. It seems that yeah, many people sort of like focused on other parts, local search or crossovers, but yeah, this is where we focused on. So basically, just to recap, binary the selection is for selecting a parent for the GA algorithm, and in the original form you randomly choose two, and then you choose the one with better fitness of the two. So here I show an example of a pool of 5 members. And if you just do the math, what it does, what binary tournament selection does, is to give different probabilities. So the best one gets 40% and the second one gets 30% and so on. So it makes sense. You want to give higher probability for the candidates who have better fitness. But there's no real reason to for the probability distribution to be linear like this, right? Like, so there are options that you can play with to optimize the end result. So for example, you can just use 3-way tournament selection where you randomly choose 3 and then choose the one that's the best. And then you get this different probability distribution. And you can just use 1-way, which is just selecting one randomly. So everyone gets the even probabilities. So you have these different options for the selection part. So what we did was we changed it so that initially we're just gonna use 4-way tournament. So the high rank candidates gets to choose more frequently at the beginning. And then as you just repeat the HGS iteration, and if you see no improvement, we slowly switch it to 3-way, 2-way, and 1-way, so that you get more exploration before reset. So that's our scheme for static problems. And next, we're going to explain the dynamic problems. So here we use modified HGS cost function, and then we use lazy dispatch. What it means is, so we are just going to use all the nodes that are given for each epoch and just use the HGS and generate routes. And then you see which one is the most dispatch ones. I mean, you've seen this before. So, so you only return the one that contains must dispatch and you ignore all the other nodes. So that's pretty simple, right? And what we added to here was that we are going to change the cost that the HGS uses. So instead of just the total distances, we're going to try to minimize the total distance over the sum of priorities, where we are assigning a priority number for each node. So in this example, the the cost the HGS calculates for this route is A plus B plus C plus D divided by 1 plus 0.5 plus 1. And let's say we have assigned 2.0 priority here, which means including this node will cut down the cost by a lot. So this is just a demonstration of how assignment of priorities to nodes controls which nodes get to be chosen and which nodes get to be deferred. So yeah, so all we need is a good formula that tells us what priorities use for each node, and we're too lazy and we want to use AI. So we have this neural net where we throw in all the information of a node, and then it outputs probabilities for different options for priority or values. And then following this probability, we're going to just choose one priority value. And we need to train our neural net. So we're using reinforcement learning. And thanks to this paper up here, we know how to train this neural net. So basically, we use same instances and we solve the same instances over and over. But each time when we solve it, we're going to have different solutions because the neural net outputs different the priorities. And then after you solve them, you see the result, and the good ones, well, actually this one, good ones, you reinforce the neural net, and for bad ones, you make the neural net weaker. So at the end, you tune your neural net so that it always, well, it has high probability of outputting a good solution. So at the end, we get 10% improvement by just using this reinforcement learning method. So that was it, and thank you for listening.
Okay, so thanks a lot for this very clear overview. Are there any questions from the audience?
Maybe just a quick one. So how many training epochs did you or did you train the model for? How long until it converged?
I don't know the counts, but it was trained for 20 hours on our server.
Okay, thanks.
Yep. But it's a big server. It has lots of CPUs and lots of GPUs, but still 20 hours, yeah.
Yeah, so because oh, sorry, any shout?
Oh, go ahead.
So for each gradient step you do in your optimization, you have to run this hybrid search, right?
Yes.
Yeah.
So that takes a lot of time. That's why we needed more CPUs than GPUs.
Yeah. So I wouldn't call that the lazy approach, honestly. I think it's quite impressive to do that and to get that to
it's the machine that does the work.
It's very expensive. Yeah. But
did your model inference turn out to be really quick, or did you use the GPU on the inference?
Oh, we use GPUs for the inference as well. But I guess it's not really necessary for the inference part.
Okay. So I think we have to move on to the next team, which will be miles to go before we sleep. So Brandon Rees, but so thanks a lot for this presentation, and we can have further discussions after.
All right, I think I'm sharing now.
Yes, go ahead.
All right, let's go. Hi, I'm Brandon Rees. I'm representing a team of colleagues working at SAS in areas of optimization and graph algorithms. Today's talk is organized to share 3 aspects of our team's ideas. There are many good ideas that simply haven't worked yet, and others that we didn't have time to show. So refer to our paper and GitHub for these. Let's go. I'm skipping slides here. Measurement and benchmarking were key for our team. This allowed us to convince ourselves whether experimental changes were actually improvements. So here's a screenshot generated by the profiling tool we used. Both profiling and static analysis were helpful to identify where the baseline solver implementation might have room for improvement. One thing that made measurement difficult was non-determinism. So our team, like many others, noticed a large variance in the score obtained between identical runs. So finding and fixing the undefined behavior bugs that cause non-determinism was a big step forward. Some of these bugs were identified by static analysis tools. Others required careful inspection of the code. I'll just show one code snippet that had 2 potential issues. The first issue is loop over an unordered set in combination with the next bug. This leads to undefined behavior because different runs may iterate this loop in a different order. The second issue is the integer overflow due to what most likely is a typo that to insert should be from insert. So here's just a diff to show how we fix the issues. We swapped out the unordered set by refactoring to use a vector of Booleans, where each unplanned task is marked with true. Also, rather than treating the first and last positions on the route using special code, we've refactored to handle them within the for loop itself. We handled the edge cases by inserting the depot directly, which I think was the original intention. Once we fixed these and other minor issues, we found that the same deterministic sequence of solutions was found each time we ran the code. This made it much easier to measure the efficacy of small enhancements. I'll also briefly mention our approach to selecting small subsets for testing, which we used to do like rapid iterations. So the main idea here was that we could do better than selecting an arbitrary subset of the 250 instances by solving a maximum dispersion problem. This allowed us to ensure that small subsets of instances that we use for quick testing were representative of the full set. Next, I'll move on. We realized that early on that speeding up the code was a great way to improve our scores across all instances, especially static scores. Note that now that we were generating the same sequence of solutions with monotonically decreasing costs in each run, pure improvements to the HGS runtime were guaranteed to give the same or better score for each instance. Listed a few ideas here, but for the sake of brevity, I'll show an example of the data structure that we swapped out. So replacing this multi-set of pairs with a multi-set of doubles and an unordered map lookup table allowed us to do the following. So eliminating the while loop in favor of the map lookup had an effect of speeding things up by 5 to 6%. Now I'll pivot to our successful attempts to improve dynamic scores. First, I'll mention a simple post-processing rule. If HGS found that any route contained 100% optional clients, we decide to postpone them to the next epoch. The pre-processing heuristics we used were also quite simple. Intuitively, the best optional clients to dispatch immediately are those that can be scheduled on the way to or from a must-go client. The worst clients to dispatch are the outliers, far from any must-go. We used both angle and insertion distance to quantify nearness to the nearest must-go client. So once the selected heuristic measure is calculated, we select the lowest ranking of those optional clients as our dispatch subset. To size this subset, we used one of three methods. Here are the three methods. The combination that worked best overall was the insertion distance heuristic with a fixed threshold. So eventually we scheduled this threshold per epoch and arrived at our best and final submission. All right, thanks all for your attention. We'll open the floor for questions.
Yes, I have a very quick question. Brandon, so you made quite a number of fixes and improvement to the code. I noted that some of these improvements related to parts of the code that were actually modified by the water team for the VAP type TW adaptation. But I have seen that other parts relate to the original AGSC VAP code and could be beneficial to that code. If you have time to chat with me or to make a pull request or indicate this improvement in the original code, it would be much appreciated, because this would permit continuous improvement of that code base and make sure that for the future is better. And for the rest of the teams who have found similar improvement that contribute to improving the SGS VAP, I encourage you to contact me either by email or directly on the repository with an issue or a pull request. And we can, for example, put a small performance improvement to the code as part of the new releases with the mention of your paper along it, such that everyone gets credit for improvement to this method. I really appreciate all the fine-tuning on improvement that you are doing on this code base.
Certainly. Yeah, we'd love to collaborate in that way.
I wanted to add, like, thanks a lot for like fixing some of the issues. I feel a bit bad that I set you up with this code, right? So in my defense, it was like done during a hackathon, so it wasn't like polished in that sense. And so this non-determinism, that was like on my plate as well. So I'm really happy you fixed it. Like, ideally, I wanted to resolve this before the competition, but just didn't have time for that. So I'm grateful that you figured this out. And so I wondered, like, in total, like, what was the like performance, like the speed up you got overall after all the improvements?
Average across the 250 instances. Well, that's the thing. How we measured it was a couple different ways to do it. So one way is to say that the sequence of we stop at the 20th solution that's generated, right? And then the 20th improving solution takes 60 seconds in the original code. If we choose that same stopping point, then we got about a 10 to 12% overall speed up. So yeah, another thing that I didn't mention in the talk that was just kind of a freebie was that we could force HGS to stop immediately. So we didn't have to put the buffer, couple second buffer, to allow for conservatism. So by using the OS timeout function, we were able to stop immediately, and that also gave a fraction of I guess a 1 to 2 second improvement. So yeah. How it played out in actual instance improvement to instances, we saw that roughly 50% of instances were seeing some sort of small improvement on static, and the other 50% were unchanged.
Yeah, okay. Yes, maybe final quick question, but then we have to move on to the next one. But so did you make any like logical changes or just performance changes to the static solver?
Yes, we actually did make some changes to tournament selection, and we actually switched out the random number generator as well and tried a couple different alternatives, and those made difference as well. Okay, so thanks a lot for quite technical presentation. So the last one for this session, so after this we will have a break, is Team Cleopatra from Patrick Klein. So
that's us.
Hello, please share your screen if you have a presentation.
So that should work. Can everybody see it?
Yes.
Yeah, just 1 second. All right. So hi, I'm Patrick. This is Kai. And together with Leo, we are Team Cleopatra. And today we'll share with you our approach on solving the dynamic problem of the vehicle routing problem considered in the NeurIPS vehicle routing competition. So essentially, this dynamic problem comprises or entails solving a dynamic vehicle routing problem. And the most straightforward, or like the baseline rationale you'd use in a machine learning based approach, is to learn a binary decision and decide for each request individually whether to dispatch it or to postpone it to the next epoch. And then afterwards, solve a vehicle routing problem with time windows in order to determine the cost minimal routes. Now, our rationale is that it basically bases on the observation that we can instead just find prices for each instance, such that including only those customers which are profitable with the with respect to the detour that they cause in our solution gives us the same solution as the optimal baseline approach would do, assuming that we have an optimal dispatching policy. So the novelty of our approach is really that instead of, or that we try to avoid this binary decision, which is potentially error prone, and instead try to represent the stochastic problem as a deterministic optimization problem. Now, implementing this approach requires a novel structured learning pipeline, which takes as input the request set, that is just the epoch instance, and comprises a prediction and a combinatorial optimization layer. So the prediction layer, or neural network, just predicts prices for each request, which we then assemble to a price collecting vehicle routing problem with time windows, which we then solve in order to obtain the routes which only contain profitable customers that we then dispatch without further modification, so not running the HGS again, to the environment. Now, just for the sake of conciseness, we'll focus on two major questions here. And that is first, how do we actually learn the weights for our neural network? And second, how do we actually solve our combinatorial optimization problem? Now, for the latter, we have implemented an algorithm based on hybrid genetic search, where we adapt the algorithm to be suitable in a learning environment. So to be used during training, because we need to evaluate it every time or for every training epoch. So our first modification concerns the solution representation. We just add a set of requests, which simply indicates which requests our solutions serve and which requests our solutions ignore. Then we modify the crossover operators accordingly and add a mutation mechanic and additional local search operators, which deal with this new request set. Finally, we warm start our heuristic with best solutions obtained from previous training epochs.
We now focus on how we find the best prices, and we find the best prices by learning them. And we try to learn them such that the solution of a price collecting vehicle routing problem with time windows matches the Oracle solution. And how do we do that? So first of all, we calculate the anticipative Oracle solution for a complete problem instance. And after that, we retrieve for each epoch the respective epoch instance and the epoch Oracle solution. And now a natural loss would be just the difference between the PCVRP solution and the Oracle solution. But the challenge of this loss is backtracking the difference between the PCVRP solution and the Oracle solution to these prices. And to do so, we came up with a perturbed Fenchel-Young loss, which penalized the structural difference between the solutions and is differentiable with respect to the prices. And when learning the predictor with this approach, we came to the following results. So in this figure, we see the gap of various benchmarks to the Oracle solution. The gap of our pipeline to the Oracle solution is around 4%, and the gap from the second best benchmark to the Oracle solution is around 20%. So this means that our structured learning pipeline outperforms all benchmarks that were provided to us. Although literature on stochastic optimization indicates that imitating an Oracle strategy fails to generalize. So still, in this case, imitating the Oracle strategy works well, and we reach near optimal solutions. And thanks a lot for your attention, and we are looking forward to your questions.
Yes, so thanks a lot. So are there any questions from the audience?
Maybe I can ask question.
Sure. Yeah.
Yeah. So for the supervised learning part, so I wonder how many samples you need in order to learn a good so have a good performance, and what is the architecture of a neural network you use?
So we only have around like 20 training instances that we consider, and only like they generalize pretty well already, like the learning. And like the training instances we use, they also only consider 50 new customers entering the system in each epoch. So the instances that we use for training are even smaller than the instances we finally use for evaluation, but the structured learning pipeline generalizes quite well over the training instances. And the architecture of the neural network is pretty basic. So it's just like, I think it's 5 layers, and each layer only having 10 nodes. So it's a pretty basic feed-forward neural network.
Nice approach.
Okay,
Yeah,
so
nice follow up on that question. So the 20 instances, did you also try several different instance seeds?
Yes, we actually did. So we by saying 20 instances, we mean 20 instances of the dynamic problem. So I think we only have 4 static instances actually, which we sample from. So those are just different seeds really.
Cool.
But so you do that like repeatedly, like you train for many epochs as well? Or do you only train on each instance once?
We train, like we have a supervised learning approach, so we just have several epochs. Yeah. So we train on them multiple times. Yes, we basically guess some weights. We run our HDS or we run our pipeline. Then we calculate a gradient, backpropagate that, and then we do the same thing again until we converge.
But do you need to run like an optimization for like every gradient step?
Yes, that is why we have limited the. I mean, it's still quite fast. So I believe we were able to train the network in 20 hours or something like that. So it's still faster than using a reinforcement learning based approach.
Yeah.
But of course, yes, we do have to run the PCHGS for each epoch.
Okay, because then I want like, can you also just, if you need to run it every time, just sample new instances, or why do you then only use a small set of instances? Is there like something you save, or is it because it's easier to train on the same instances?
There is still the time issue, I would say, because we always have to include in each evaluation, we have to include this perturbation. So in order to backpropagate this gradient that we have in this loss function, there's this set.
Yeah.
And the set is a perturbed vector. And we include around 20 perturbations now to calculate the expectation. So each evaluation we have multiplied with these 20 perturbations to retrieve the gradient.
Yeah, okay.
Maybe
that's for discussion offline. Like I'm curious how you do this exactly. But I want to say I think it's very nice, nice strategy indeed. That's it's sort of what we try to provide in the supervised learning baseline as well, like learning from the Oracle, let's say. But you resolved like the obvious bottleneck there that these binary decisions are very hard. I think in a very elegant way. So nice. Okay, I think that's for this part of the session. So I propose we have a small break now until like 10 over the hour. And then we'll have last 3, because there's actually one team that does not present their approach today. So we have 3 more presentations, and then we will go on to the results and the prize ceremony. So I'll see you back in 8 minutes. Hello. Welcome back, everyone. I hope everyone is here. We can maybe wait for very quick. So the next presentation will be by Team HusSmart. I think you now will present. So can you share your screen?
Hello, can you hear me?
Yes, I can hear you.
Hi, everyone. Can you hear my slides? Can you see my
Yes.
slides?
Yeah, we can see them.
Hi, my name is Xinhao Li, and I'm honored to be here to present the algorithm used in this competition. Since everybody has a very clear definition of the problem, so my presentation mainly introduce our algorithm, including the static variant and the dynamic variant. And finally, I will introduce our team. We improved the solver based on the algorithm in baseline HGS VHW. The main improvements are as follows. First, my slide. We improved the solver based on algorithm in baseline HGS VHW. The main improvements are as follows. Firstly, a crossover EX was implemented, which is considered together with the two existing crossovers, and then use a penalized cost function to find the best offspring. Then, if a new best solution is found, the SISR algorithm is to use further improve the solution. Finally, after NBI iterator consecutive local search and the algorithm not improved, we use the DLSMA algorithm to improve the population. This algorithm is we used in Dymax competition. The EX crossover is published by Nagota in his paper in 2010. The process of generating offspring of EX is divided into 3 steps. The first step is to generate the JAB. JAB is a set of ages that each age in a JAB appears only one time of the 2 parents. In the second step, use JAB to generate an AB cycle. In each AB cycle, ages from 2 parents appearance alternate. So there are even number of age in one AB cycle. The third step is to apply AB cycle to a parent. Remove the age that originally belong to 8 and end the age that don't belong to 8. In this solver, the select introduction by string moves were used, which is called SISR. We implemented random selected customers, read lane selected customers, and string removes. The neighborhood structure is larger than the relocate and exchange. Each time, about 15 to 20 customers are removed from the solution. These customers are reinserted into the partial solution later. We also try to improve the OX crossover. The process of OX crossover in HGS is to randomly inherit continuous customer from first parent and fill the remaining customer into the offspring in the order of the second parent. We only change the first step, we just to inherit n fragment customer from the first parent. N is the remainder number range from 1 to m, which m is the number of rows of the first parent. Let's move on the dynamic variant. The algorithm we use is very simple. The most important decision for dynamic variant is to decide which customers to postpone to the next epoch. For a customer, the following 6 variables are available. We try to weight and sum all the variables. Each variable is multiplied by its weight and then summed. The weights are adjusted according to the experiment results. In the end, we found that just use the latest arrival of time window and the declaration from depot is enough to make decision very well. So the penalty I donates the penalty value of the node I. Latest arrival node I donates the latest time of the time window of node I. Declaration depot I donates the distance of node I to the depot. The ABC are the constants. The constants ABC are obtained from the multiple simulation of all the instances. Then the node information and the penalties as the input for the OR tools, and solve the problem with the method penalty and drop-in visits. The feasible solution and the collection of deleted customers can be opted from the OR tools. Finally, the remaining routes are input as initial solution to the static solver. Finally, let me introduce our team. They are our team members from this competition. There are 6 people in total, including my monitor, Professor Lu. HUST means my school, Huazhong University of Science and Technology. SMART is name of my lab.
Okay, so thanks a lot.
Our team.
Oh, sorry, I thought you were, sorry.
Our team focuses on the basic algorithm theory of intelligence, machine learning, reinforcement learning, solving the complex systems, and promotes the wide application of the intelligence optimization technology in the industry. So that's the end of my presentation. Thank you.
Okay, so now sorry for interrupting a bit early. So thanks for your presentations. Do we have any questions from the audience? So I had a question. So you have this method of penalties and dropping visits from OR tools?
Yes.
Can you explain, is that, like, I think similar to this price collecting TSP that we've seen before? It's just like you get the penalty if you don't visit certain customer.
Sorry, I don't understand. Do you just mean the penalty function?
So you said with the OR tools you solve the penalties and dropping visits. That is just
Yes,
like
yes.
heuristic optimization method for the VRPTW, but you get a penalty if you don't visit certain customer. Is that correct?
Yes.
Okay, and then after that you solve the problem still with the hybrid genetic search.
Yes. After that, we just solve it as a static variant.
Yeah. Okay. And you had the DLL SMA algorithm. I saw like in the hybrid genetic search. Can you quickly say what that is?
Yes, this algorithm we use it in the dynamic competition. We get the second place, yes, in the dynamic competition.
Ah, okay. Okay, then thanks a lot. Let's move on to the next person, which will be How to Route from Juan Pablo Mesa Lopez, if I pronounce it correctly.
Yeah.
Are you? Yes.
Okay, I'm trying to share my screen.
Can you, or do you need some rights still? Yes, we're seeing your screen now.
Okay, so we are team How to Route. We will propose a modified HGS for static VRP with time windows. and a simple neighbors addition and postponement strategy for the dynamic variant. We are 4 members from Universidad EAFIT in Colombia. I'm Juan Pablo Mesa, and my colleagues are Alejandro Montoya, Alejandro Uribe, and Camilo Alvarez. For the static variant, we use the HGS that you guys provided in the baseline for the challenge. And we did some modifications to the local search and to the genetic crossover operators. So in the local search, the main change that we did was, given that the swap star and relocate star are computationally expensive neighborhoods, we decided to reduce the amount of times that these neighborhoods are explored. So the intensification probability was reduced from 15% up to just 3%. And with the limited computation time that the computation has for the instances, this accelerates the convergence of the solver towards lower cost solutions. In the genetic crossover modifications, what we did is we added an additional crossover operator that is called adjusted order crossover operator. It was published this year by Vatum, I hope I pronounced that correct. And the idea is just to take the order crossover and modify it to start the appendment of customers at a different place to avoid scrambling a lot the solutions when the crossover is done. And in order to include this new crossover operator in the solver, we had to add 2 new offspring generations instead of 4. So now we have 6 offspring generated each time that we are going to create a new individual. For the dynamic variant, we tried a simple approach. The approach consists basically of 2 main phases. One phase of adding non-obligatory neighbor customers, and a phase of postponing neighbors that were previously added that would worsen the solution. And in between those 2 main phases, we perform 2 routing steps. One when after adding the neighbors, and one after removing the neighbors that would probably worsen the solution. So graphically, I could explain it a bit better. So we got an instance with some customers that are not must dispatch. The red ones are the ones that the epoch indicates that are must dispatch. Here's the depot. So the idea is that we're going to run a k-nearest neighbor strategy, and considering the neighbors are nearby the must dispatch customers and that their time windows are more or less similar to the time window of the must dispatch customer, we're going to mark that customer as a customer that should be routed. We perform that several times, and then what we do is that we solve that solution with the static solver. And after we get this solution, we try to calculate which customers are the ones that add a lot of cost to the solution. For instance, this customer here adds a lot of cost to the solution. So we remove it. And after removing it, after removing some of the customers from the routes, we rerun again the static solver, and that's the final solution that we deliver. So yeah, those are our strategies. They were pretty simple, but they gave good results for this competition.
Okay, thanks a lot. So are there any questions from the audience?
Just a question of simplicity. I see that in the VIP time Windows code, there is 2 different crossover, and one of the solution is kept as the next one. In your implementation, you are using 3. Have you done some ablation analysis to see whether the 3 crossover are really necessary, or if a single one would be sufficient to achieve good result? For example, the new one by itself could be perhaps a very good option.
We explored the 3 of them. Yeah, we did the ablation studies to see if only one of them was better, but we found out that having the 3 of them at the same time, it's better, well, gave better results than just using 1 or 2 of them.
Yeah, because I think that relates to a question I was having. Like, do you know how often the different crossovers get selected?
No, I did not collect that information.
Okay, because I think it's based on like the quality of the solution after you apply the crossover, right? So then,
yeah,
I think we didn't do the analysis either, but it's like I would expect this like the crossover which just combines complete route actually to be better because the other ones ruin the solutions a bit more. But yeah, maybe it's interesting to do some analysis at some point. Apparently you find improved results, so that's good. Any other questions from the audience? Then I think it's we can move on to the final presentation, which is by Peter Dieter from UPB. Feel free to share your screen. Can you stop screen sharing, Juan?
I'm trying to find how to stop sharing.
Should be in your Zoom window, I think, on the top.
Yeah, thanks.
Are you talking, Peter? Because I can't hear you.
Okay, still not?
Oh, now it's better, but it's very
very
soft. Yeah.
Okay, then I need to speak very loud, probably.
Yeah, this is good.
Okay, let me share my screen and share it.
Yes, I can see it.
All right. Good. Okay. Yeah. So first of all, thanks to all the organizers for organizing this challenge. I think it's quite a big, big process. And yeah, so I will present to you a regret policy for the dynamic problem case. And yeah, let's start off with some notions. So you're probably all familiar with those. So we have a set of due customers. They are marked in red here. We have a set of undue customers marked in blue, and they have all a little number inside. And this number represents the orders that will be drawn, or the expected number of orders that will be drawn until the order itself is due. Then we have some gray customers from which orders might be potentially drawn. And then we have a threshold value, which I will further explain soon. So in the base policy, for all the undue orders, we do the following. So let's look at the example right here. We have order I, and we first find its closest due order, which is order D. And the distance between those two is CID. And this distance is also a very rough approximation of the additional routing costs of dispatching order I together with the other due orders. But yeah, as I said, it's very, very rough. But in the future, there might be better orders be drawn. So for example, from customers 1 and 2, and the distance here is CI1 and CI2. And the improvement from orders that might be drawn from these customers is the difference in distance between CID and CI1 and CID and CI2. So we sum up these differences, and this part of the equation is basically represents the improvements by a future customer being drawn, and or in other words, the regret of dispatching order I immediately. And we correct that by the probability that the customer will be drawn until the order is due. And we do this for all undue orders. Now we take the lowest value. In that case, that would be 0.15. That's below a certain threshold value that needs to be tuned. And we mark that order as due, and we go back to step 1 and recalculate the regret values. And now nothing has changed. 0.22 is again below the threshold value. So we also mark that order as due and recalculate again. Now all the values are above the threshold. So we stop and we use the given heuristic to construct feasible routes. I also included 2 extensions to the base policy. The first one is that waiting times arising from routing I and D consecutively are penalized, even though waiting time itself is not part of the objective function. It's still not desirable because it binds vehicles. So I add a weighted term to the initial regret value. And then the other part is that I also consider other undue orders. So the procedure here is the same as for the base policy, but now I don't look at these gray customers, but at the blue orders. And because they're already in the system, I also don't do any probability correction. And then again, I add a weighted penalty to the initial regret value. Yeah, so to summarize, I presented to you a parameterized regret policy. The policy is actually quite simple to implement and quite straightforward. And there are many possible further extensions. For example, I think a better approximation of the true routing costs of dispatching order I. Right now, I'm just using CID, which is very rough, but that could be improved. And that's it from my side. Thank you very much.
So thanks a lot, Peter. So any questions from the audience?
Maybe just a quick one. So
yes.
When you calculate the probabilities of each customer occurring, does that also include, or do you also account for which customers can actually occur and which cannot occur? Because we have some feasibility constraints, like with respect to time windows and so on and so forth.
Yeah, that's included. Yeah. So so this number, basically, there's like this number here, like the 22, for example, or 99. I calculate that by looking at the time windows, and also because we know that 100 customers or 100 orders are drawn, right? So this can basically be calculated logically.
Yeah, because we had a similar thing. Just out of curiosity, how much computational time did that take? It's quite quick, right?
To calculate the regret, just one single time, you mean, or in
calculate probabilities, essentially.
It was very quick, but I didn't measure it, but it was very quick. So I think yeah, milliseconds, basically, like yeah.
Okay, I also had a question, because I think it's quite nice. You use actually the distribution information that you have, right, to compute this probability that you will get certain requests somewhere. So I think that's very clever in the context of this competition. I think in general, like in practice, it's a challenge to like know the actual distribution. Like, do you have a feeling how important this is, or could you use, like, let's say, like black box sampling based approaches as well, or do you really need to like have an accurate explicit distribution?
Yeah, so I mean the method itself, as you said, it's really based on the distribution that is given. So I cannot really tell you how sensitive it is to, yeah, if there might be new customers coming in that I don't know. But for example, these numbers, because I also had some I think like a bug in there that doesn't calculate these numbers here, right, like 22 and 99. So at least from that perspective, it was relatively robust because the change there was not even that big. But yeah, I mean, then when I do basically the this step, calculating these distances and difference, then I really rely on the distribution.
Yeah. Okay, thanks a lot. So I think that brings us to the next part of today's workshop. But first, I want to thank everyone for presenting their methods, which I think were very nice presentations, all very clear, and you've done amazing work. Okay, seeing some chat here. Let me share my screen to go to the announcement of the results. I'm looking for the button. So you can see my screen, right?
Yes.
Put this on a different window. Okay, so to start, there are like different types of results and prices. So one I already mentioned during the small introduction and competition overview are the leaderboard prizes. So I didn't want to spoil this, but of course this was public information, so we already went over it, but I want to take some extra time to congratulate actually all the teams. My computer is a bit slow. Who scored the leaderboard prizes. And so this will be these 5 teams which will get these different prizes, and so we'll be in touch about distributing the prizes. So let me then move on to the next part, which is the final ranking. So I will reveal first the numbers 6 to 10, and then one by one we will go from 5 back up onto the top. And so these are the ranks we did by running your submissions on like 100 new cases. And so number 6 to 10, these are those teams. So Team Dynamo, we have UPB, then we have the Kirchhoff's Law, How to Route, and then Roberto Hood. And you can see here like the different ranks for the static and the dynamic problem and how this affected your average. And here for the tiebreaker, we have overall average cost. I want to say now it looks there's like there were 50 teams, so whichever position you get in the top 10, I think you've done amazing work. Okay, so then number 5 is Miles to Go Before We Sleep. Then team number 4, it is Hust Smart. And then team number 3, it is Team SB. And so now maybe you can already do some like inference, but to announce a final result. So this is between Team OptiML and Team Cleopatra. And Team OptiML got second, which means that Team Cleopatra is the winner. So I would want to congratulate you all very much on this. To make a small comparison to the baseline, or the best baseline basically we provided was this greedy algorithm. And so for the dynamic problem, you saw that you were able to, like, let's say more than 10%, even like 13%, I think, improvement over the baseline, which I think is really amazing. And for the static problem, these numbers were quite small. I have to admit that maybe in hindsight we should have like used larger instances to make these numbers like a bit more difficult, or the difference is a bit bigger. But I think there is still like a significant difference in results. And so that means that the prizes will be as follows. So for the first team, it's 22 euros. Too bad the competition doesn't finish next month, right? For OptiML, that's like 750, and for the third team, it's 500 euros. And then we have some additional awards, actually, which is the Young Talent Award. This is awarded to the best team, which consists of only PhD students. And this is actually, hello? I'm very scared that I clicked too much at one time. This is also Team Cleopatra. So not only first prize, but also best student team. So congratulations on that. I'll give you in a moment a bit of time if you want to say something. And so then finally, the last category is the jury prize. So if you read the detailed rules document, we had some constraints for the jury prize. So this is awarded to the team that offers a novel solution approach, uses machine learning, achieves good performance, and maybe it's a bit unfortunately for Cleopatra, does not win the first place, which means that this prize will go to Team SB, which I think which was only the only other team I think which used also machine learning and got like very good performance. So congratulations on that. So that sums up pretty much all the prizes. I want to make some final remarks here. So I want to thank you all very much for participating in this competition. In all honesty, it was a lot of work also for us to organize. It was more work than we expected, but it was definitely worth it, seeing all the excellent work that you did on this. You exceeded my expectations. So we had a bit of discussions also with the organizing committee, like how we should set up this competition with this different tracks. So the idea was really that we wanted to have this like overall leaderboard to test, let's say, also the versatility of methods. I think in the end, many people use like specialized approaches, right, for the dynamic and for the static problems. So that's maybe something we should consider for the next time. But I think it's nice, it encourages all of you to work on both of these problems and see so many things come out of that. And I have looked at the papers that you've written, so they will be published soon. But this was really excellent work, I would say. And so I wanted to say, so this was part of NeurIPS, right, which is a machine learning conference. And so really the goal was to, well, also encourage machine learning based approaches, whereas I'm not fond of just enforcing this, because then it's very easy to just put in some machine learning model somewhere which doesn't actually do something. So we try to encourage it. And I think it's very nice to see that actually, if we look at the ranking, let's say for the dynamic variant separately, then the number 1 and number 2, this was Cleopatra and Team SB, it's both machine learning based approaches which use a neural network, I think somewhat similar to predict certain values for the different orders. And it's really nice to see that this can actually outperform them by quite a lot, all the others which are more based on sampling type of techniques. And so thanks a lot for all the improvements you made to hybrid genetic search. So I think Thibaut is indeed very happy if we could contribute it back to the original repository. We will also see if we can like get some of this back into the VRPTW variant. But I think this was amazing work. So the results will be published on the website, as well as the papers and the slides, and hopefully, if everything went correct, also the recording of this workshop, so that will be available on the website. No, the recording will be available on the NeurIPS website, actually, because we have to play by their rules, but after some time, I hope we can release that, or that will be public in general as well. And so I'm looking very much forward to seeing your future work, to see how you will build on all of this. And so regarding the paper, so we will publish them on the website, but this is not like an archival publication. You're free to extend your paper and submit it to a venue. And I think Thibaut can make some announcements regarding to that. Can I invite you to
Yes, absolutely, Walter. So indeed, the papers on the website are just like short papers that are not for archival. We have discussed with the organization of the DIMAX challenge that took place a few months ago, and there was 2 special issues related to the DIMAX challenge, which were the informed journal computing and transportation science. The informed journal computing already by design was open to more submissions that went beyond DIMAX challenge. So you can obviously already submit there if you opt to go with the iJoc. And we have been discussing with the editor-in-chief, Karen Smilovitz, and other associate editors for the TS special issue of the DIMAX challenge, And it seems that it's very likely that we can also reopen that special issue to receive a few more papers that relate to this competition. So if you want to send your paper, your complete paper, for a potential review and transportation science special issue, it is likely to be possible, and we will announce that in the coming days by email with more instructions to do that. Just as a reminder, the iJoc has a slightly more computational experimental focus. The transportation science special issue is a bit more methodological oriented. So all reviewing is going to be done according to the standard criteria of TS, which is to look definitely at the methodological contribution, impact, and computational performance. So thank you all. And yes, so happy to see contribution to HGS. There is a dev branch. Don't hesitate to do some pull requests and to communicate with me. Thanks a lot, everyone.
Yes, and so one more thing that I can add to that. So we will also write a paper just describing the overview of the competition, basically following up on this rules document, which I think will even be part of like transactions in machine learning research, or like PMLR, like the proceedings of machine learning research, which is like for all the NeurIPS competitions will be published in that way. So you can cite the competition also in your paper, which is appreciated. Yes, so now I wonder if there is someone who likes to make a comment or like speak maybe to the winners. And after that, the plan was to have breakout rooms, but I think Laurens, now you are host. I'm not sure, are breakout rooms enabled? Because I think there were some extra steps which I did not get to yet. So we can also schedule a short break, and I can see if in 5 minutes we can go back for some breakout rooms.
I didn't look at that, but I can also make you host again, Wouter.
I'm sorry, you can?
I can also make you host again, but I don't see any easy option for breakout rooms.
No, I think I need to enable. It's a bit annoying, like we got a special account from NeurIPS. Yeah. I need to log into that and enable it. Okay. But first, is there someone who, like, we can also have a small general plenary discussion, because we're just 26 people now, I think.
Would you like? The room is fine. We are 25 now. We should be able to communicate.
Yeah, we can also do that. So yeah, maybe let's not break up them, but maybe to start with the winners. Patrick, would you like maybe to make some comments or like share some thoughts?
Well, first of all, maybe we'd like to thank the organizers, of course. So you had this nice prize of the jury, right? I think that you as a jury deserve a prize as well. So we had a lot of fun with the competition, especially this dynamic leaderboard. I suppose it had some, it resulted in some sleepless nights for some people.
But I'm happy you appreciated that.
Yes, so thanks a lot for organizing everything and providing the resources, and of course giving us the opportunity to do this kind of research, right?
Yes, okay, so yeah, thanks a lot for making good use of this. So it was definitely worth the effort, let's say that. So maybe for a second team, Niels or Casper, does someone want to comment? Don't want to push you, also feel free. But
do we is the recording enabled until the end? Because if we want to have more social discussion that don't appear in the recording of NeurIPS, we could have this thing without thinking, oh, this is recorded, and people will cannot consult this forever.
Okay, I can probably.
I can stop the recording at any time.
Yeah, I think if we want to have more social interaction, it perhaps favors more.
Let's stop the recording. So for the people watching the recording, thanks a lot.
Yeah.
What happens now will be for the people who are there live.